Welcome to another simple engineering snippet. In this instructional video, we will use conservation of energy to calculate the power output from a hydraulic turbine. I hope you find it useful. Here is the problem statement and the corresponding picture of the system. A hydraulic system is hooked up to a tank that supplies water via gravity. The heights, diameters, and the velocity are as indicated. The efficiency of the turbine is 0.70, and the hydraulic losses for the given conditions is 8.5 feet. Let's label some points. The free surface of the water in the tank is point alpha. The inlet and outlet of the turbine are points Bravo and Charlie, respectively. The location where the pressure gauge indicates 17 pounds per square inch gauge is point delta. Let's review conservation of energy in a steady flow system from point 1 to point 2. The mechanical energy at any location consists of the pressure term, the kinetic energy term, and the potential energy term. Conservation of energy says that the mechanical energy at point 1 is equal to the mechanical energy at point 2 plus any energy loss and energy loss due to work output. If there were no energy losses or work output, then the energy at 2 would be equal to the energy at 1. We are working with head, which has dimensions of length. Head represents energy per weight. We want to determine the power output. Power can be calculated by multiplying the specific weight of the fluid with the volumetric flow rate and the turbine head. Now let's apply conservation of energy from point alpha to point delta. The pressure at alpha is atmospheric or 0 since we will be working in gauge pressure. The velocity at alpha is 0 since it is a large tank. The elevation at alpha is given as 100 feet. The pressure at delta is given by the pressure gauge and is 17 pounds per square inch gauge. The elevation at delta is 6 feet. The head loss from alpha to delta is given as 8.5 feet. Our first step is to determine the turbine head. Looking at the equation, I see that I need to point out that the velocity at point delta is 25 feet per second. Let's solve the equation for the turbine head. Now we'll plug in numbers and units to obtain that the turbine head is equal to 36.6 feet. This is not the final answer. We are seeking the power output from the turbine. To calculate the power, we need the volumetric flow rate, which we can determine from the velocity and diameter at point delta. The volumetric flow rate is 4.91 cubic feet per second. Now we have everything we need to determine the power the fluid is supplying the turbine. Using units and a conversion factor, we obtain 20.4 horsepower. That is the power the fluid is supplying the turbine, not the power output from the turbine. We are not quite done. The turbine efficiency is given as 0.70. The definition of efficiency is typically a desired output over the required input. In this case, the output is what we are trying to calculate. We have already determined that the input to the turbine is 20.4 horsepower. Solving for the turbine output, we obtain 14.3 horsepower. This is our final answer. I hope you found this instructional video useful. If so, then please like and subscribe. Thanks, and have a great day.